Greetings humans, my name is Garuda, and welcome to a tutorial on Kugelblitz. This is a boss module. Just erase these notes. This is a boss module, so in case you are not familiar with what that means, every time we solve a module, this module is going to change and going to display new information, and then at the very end of the bomb, we have to calculate the answer and input it. So this is Kugelblitz. This is what it looks like. You'll see a big black sphere in the center, and other orbiting orbs around it. And what we're going to need to do is, for each of these stages, just get a 7-digit binary number from the orbs that are rotating around here. Now, if you are comfortable with it, I definitely suggest enabling colorblind mode. It will display the orbs and their states in the center here. I won't be using it for the purposes of doing this as legitimately as possible, but it definitely makes the module a lot more reasonable to do, as this is a very tough boss. So the binary that we need to extract is in RGB order: red, orange, yellow, green, blue, indigo, violet. Ignore my notes down here. That's when I do voice bombs. And we're going to associate each of these with a 1 if that corresponding sphere is colored. So in this case, it's a bit too hard to see. They're moving very quickly, but there is no red. That one they just looped over there, this one, that's actually orange. So there is no red sphere, so the red is going to be 0. Orange, as I said, that's the one that's looping like this. So there we have an orange. Yellow is this one, that one that's going around like that. Green is also present. It's going very quickly around right there. Yes, so we have a green. Blue, you might think that that's blue. It's not. That is indigo. Blue is a more azure color. We'll probably get an example of it. So this is indigo. So blue we do not have. Indigo we do. And then violet is a purplish color. We don't have that. So our binary we get from this stage is this. And that's all we need. We just write that down and then go ahead and solve the module. Moving back here, we see that the spheres have changed color. So we need to get another 7-digit binary. There's no red. There is no orange. We do have a yellow orbiting right there. No green. We do have a blue. See, that's that azure color I was talking about. No indigo. No violet. Now what we need to do is we need to XOR these two strings. XORing basically means that we compare each of the positions. If it has a single 1, it becomes a 1. If it has 2 zeros or 2 1s, it's a 0. So in this case, 2 zeros is a 0, 1 0, that's a 1, 1 1 is a 0, 1 0 becomes a 1, there's just 1 1, that's a 1, 1, and a 0. So that's the result of our XORing, and that's all you need to do each stage. It's not that bad to do as a boss in that respect. Solve another module and get some more binary. We have a red. There is no orange, no yellow. We do have a green, that quick one rotating there. No blue. We have an indigo, that one right there, and no violet. Now we're going to XOR this here. So you'll notice this is what the result. This is the result of the XORing of these first 2 stages. You basically just you XOR the first 2, get a result. XOR the third with that result. Get something else, XOR the fourth with that. You just XOR all the way through. So this becomes 1 1 0 0 1 0 1 0 0. Yep. And then if there were more modules, this would just keep going. We'd just continue XORing with the current value until you get to the end. I believe if you miss a stage, you can intentionally strike the module by clicking on it, and it will display the previous stage that was given. So if I haven't done it on this bomb, I'll demonstrate on a different bomb, but if you miss it, you can take down the current stage, then strike the module, and then take down the previous stage. But you have to do it immediately afterwards. There's no way to retrieve stages if you are 2 behind, I believe. So that's definitely something to watch out for. So solve this, and the module goes into submission phase. For the submission phase, here's what we need to take down. all we need is the number of colored particles. So in this case, it's a bit hard to tell because they disappear into the background every once in a while. So you want to wait till all 7 are present on the screen, which is not right now. I only see 6. There we go. It was present for just 1 second. We have 7 violets. So this is violet, by the way. We didn't get a chance to see it, but this is what the violet color is. I definitely, you kind of just have to wait. They're all present now, or they were for like half a second, because they do disappear into this gray background. So we have that 7 violets, and now you just let your expert do all the work. That's all they need from the module. So I'm going to pull this manual out here and get started. This final binary, we need to split into 3 parts. The first part is going to be labeled R, second part is X, and the third part is Y. And I'll explain each of these as we get to it. Basically what we are going to be doing is ending up with a sequence of 21 binary digits by the end of this that will correspond into an input that we need to put into the module. But that's a long ways off. So first thing we need to do is convert both of these into decimal, which is not hard. It's just a 3-digit binary number. I can count. So this is 4 and 4. And these correspond to coordinates in this grid right here. X moves you left to right, Y moves you top to bottom, and these are 0 indexed. So in this case we have X is 0, 1, 2, 3, 4. That's the 4th column for X, and Y is 0, 1, 2, 3, and 4. We start there. So this is our first position. Now, what we're going to be doing is very similar to black hole, in that we are going to get some digits, add them together, and move in a certain direction, and then rotate, and then get some more digits, and each time we're going to be getting 1 more digit than the last. However, this is unspeakably more complicated than black hole, for various reasons. The first thing we need to do is to determine our initial direction, and this comes directly from the colored spheres we have. Referencing this line right here, our direction is that number of colored spheres times 45. That is the number of degrees, or just rotate from north 45 degrees for every colored particle. So 1, 2, 3, 4, 5, 6, 7. We are facing up left. So this is our direction. We aren't actually moving there. I'm just highlighting it to show you. So we're facing northwest. I'll put that down there. That will change very soon, but just as a reminder. Now, for the first digit, what we're going to do is add the digit of the square we are currently on, and then move once in the direction that we're facing, and then output the result. That's all there is. Note that we add and then move, so you do not, we started here. We don't move and then add this 0. So the first digit isn't 0, it's 6, because we add what we're on and then move to the next square. And in fact, this 0 does not get factored into the calculation. Of course, it wouldn't matter. But let's say we were here, right, and we were moving up left. The first digit would be 2, it wouldn't be 4. This square that we moved to does not matter. Right, in this digit, of course. So we are now right here. We are facing up left. Our first digit is a 6. Now we need to rotate. We always rotate 135 degrees. However, the direction we rotate is dependent on R, which is this value here. R is obviously 1 or 0 because this was from our final binary number. If R is 0, we rotate clockwise. If R is 1, we rotate counterclockwise. So we're going to rotate 135 degrees counterclockwise, which is 3 45-degree steps. So we're facing up left, 1, 2, 3. We're now facing downwards. Now, for our second digit, we add the value of the current square and move. Add the value of the current square and move. We do this twice because we're on the second digit. You do it a number of times equal to the digit you're on. We did it once for the first digit, twice for the second. So the value of the second digit is 0 plus 2. Once again, this 5 that we're on currently does not matter because we add and then move. Second digit is a 2, and we are facing here. We are moving down. We rotate 135 degrees counterclockwise. We're now facing upright. So we add 5, 6, and 6, and we end up right here. So our final square is there, but we add only these 3. 6 plus 6 is 12, plus 5 is 17. If we have a large number like that, we take it modulo 7, for reasons that will become clearer later. So 17 mod 7 is 3, because 14 plus 3 is 17. So now we are facing upright, right there. We rotate towards the left. We're rotating counterclockwise, 135 degrees, 1, 2, 3. We face left. We then add 6, plus 2, plus 3, plus 1, and we end up right here. 1 plus 3, once again this 5 does not get factored in. And this is 4 squares, because we're on the 4th digit. Hopefully this pattern is making sense. 1 plus 3 is 4, plus 2 is 6, plus 6 is 12, mod 7 is 5. 7 plus 5 is 12. So our 4th digit is a 5. We're facing left. Rotate counterclockwise. 1, 2, 3. Oh boy, I've just realized that we are in a very interesting spot here. Okay, 4-digit 5. 5 plus 0 plus 6 plus 3 plus 0. And this has not actually worked out quite as well as I wanted. Here's what I'm going to do, because I wanted to show you what happens when you wrap in this table, but we were hitting a corner, which is an edge case, no pun intended. So in this case, our next digit would be 11, 14, mod 7 is 0. So our 5th digit is 0, but I want to demonstrate some stuff first before we move on with this actual example. This table does not wrap the way you normally would. Apparently, it wraps like a Klein bottle, which is what the manual says, which is a 4-dimensional shape in topology, but that's neither here nor there and really does not matter. The upshot of that is that when you move upwards or downwards, so if you're wrapping vertically, basically, what happens is your position gets reflected over the vertical axis. So what do I mean by that? If I'm at 1 and I move upwards, I should end up at 6, but my position is reflected across this axis, and I end up at this 4. Okay? Another example. If I was at this 1, moving downwards, I should end up at this 3, reflected across this bar. We end up at this 4, and again moving downwards. The second thing to note, if you're moving horizontally, your position is reflected across the horizontal axis. From this 3 moving right, we should end up here, reflected, ends up here. This 6 moving to the left, or sorry, let's say this 0 moving to the left, should end up here, reflected across this bar, it ends up here. So that's the first complication of how wrapping works. The second thing you need to know about wrapping is that it changes your direction. So your direction gets reflected across the axis that you reflect your position across. I'll explain that. In the case that you are going up, down, left, or right, this does not matter. So in those cases that I just showed, going down from 6 would take us to this 0, and our direction would still be downwards. However, if I was going down right, okay, say I started here, I went down right, now I go down right again, I should end up at this 3, okay? My position gets reflected to this 4. That's what we've already covered. However, then my direction gets reflected across this axis as well. My direction was down right. Think of an arrow pointing down right, and then reflect that arrow across a vertical axis. So we're now moving down left. You can also think of this as just more brute force, as moving vertically swaps left and right, moving horizontally swaps up and down. So in this case here, we moved down right, that took us to there, and facing down left. An example, moving horizontally. If we are there, moving down left, so down left from that 4 should take us to, well, this is a bad example because it doesn't get reflected. Down left from this 1 should take us to this 6 right here, so it gets reflected, takes us to this 5, and then our movement of down left is reflected across the horizontal axis, and we now point up left. Now, you'll notice I just said that sometimes you don't get reflected. That happens if you land on this middle cross here, because reflecting across this, if you're already on it, doesn't do anything. So if I'm moving downwards from this 3, just straight downwards, I would just end up at this 6. Or moving down or up left from this 0 would take me to this 4. Yeah, because as it should, like that's what you expect it to do. However, if you're moving diagonally, your direction would still swap, of course. So up left here would take you to the 4 there, but now you are moving down left. With me so far? Okay, the last thing you need to know about rotation is that it changes your R value. Whenever I wrap, either vertically or horizontally, my R value swaps from 1 to 0 or from 0 to 1. So for example, let's go back to this one I was doing here. Here, down right. Let's say we were rotating counterclockwise, since that's what we had here. Moving down right would take us to 3. 3 reflects across this axis, takes us to this 4. Now we know our position, our direction gets reflected as well. We're moving down left. And also, we are now rotating clockwise. If we were rotating counter, we now rotate clockwise. Now, of course, this wouldn't matter until we get to the end of the step, because we only rotate. We don't rotate after every movement. We rotate at the end of each digit. As you saw, hopefully, way back when we were actually doing this, you rotate at the end of each digit. So it is possible that you wrap twice within a single digit, or 3 times even, and your R value goes from 1 to 0 and then back to 1, and it doesn't actually change anything. So you need to track every time you wrap. And this is true across digits. Like this, again, this is an iterative process. So if it changes in 1 digit, it's going to have changed in the next digit as well, as you would expect, right? Nothing resets between digits. Okay, the last thing you need to know, and this is what actually just came up here, is the edge case of hitting a corner. If I'm moving down right, which is exactly what's happening right now, and I hit this corner here, what basically happens is you bounce off. The technical explanation of what happens is you reflect across both the vertical and horizontal axis. So you should go to this 5 over here. 5 reflected across the vertical axis takes you to this 2. 2 reflected across the horizontal axis takes you back to the same 0 that you were on. You don't need to think about that. The upshot of it is you go from this 3 to this 0, go into the corner, and you just bounce, and you land on the 0 again. So it wouldn't go 3, 0, 3, it would go 3, 0, 0. And your reflection, your direction gets rotated. So if we were going down right, now we're going up left. So, finally we can get back to this example right here. We were on digit 5. We went 5, 0, 6, 3, 0, and now we need to move once more, because once again we move after we add the last digit. So we just bounce off of the corner. We are now facing up left on that 0. And we can continue. Facing up left, we now need to rotate. We're still rotating counterclockwise, so we end up facing downwards. 1, 2, 3. Facing downwards from this 0. Now, everything starts to get crazy. We move downwards. Well, first we add 0. So we add 0, move downwards. It should take us to this 2. It gets reflected across the vertical axis. So we end up here. Our R value now changes. Don't forget about that. R value is now 0. So now we're rotating clockwise. But that might change again. I don't believe it is, though. So we're going to go 0, which took us to this 5, 1, 4, 3, 0. Because we're on digit 6, so we need to add 6 digits. And then we move once more. We land on this 6. So this sum here, again, ignore the 6, is going to be 0, 3, 4. That's 7, so we can just ignore that. 1 plus 5 is 6. Okay. We're on that 6, we're looking downwards, and we need to rotate 135 degrees clockwise. Again, clockwise because our R value got swapped. I suppose I should have mentioned that bouncing off of the corner does not change your R value, or technically what it does is it changes your R value twice, because you reflect across vertical and horizontal, so your R value does not get affected by bouncing off a corner. which is why I didn't account for it there. But it did get affected by going downwards from that 0. So now we rotated 135 degrees clockwise. We are facing up left. 6 goes up left. We should go to this 5, reflect across horizontal. We end up at this 6. We don't move up left, though, because our direction gets swapped as well. Direction is now down left. I'll repeat that because that's the first time we've actually had to do that on an example. Up left should take us to here. It reflects to the 6, and then our direction, which was up left, gets reflected across the horizontal axis and now points down left. We have 6 plus 6, 6, 6, I just noticed that, 5, 1, now we need to move down left again. I just realized, this is why this is so easy to mess up, I didn't change my R value. When we moved from 6 there up left, our R value should become 1. It's not going to matter because we're on the 7th digit, so we don't actually have to do anything more. We only need 7 of these digits, but, you know, for consistency's sake. So we're moving down left from this 1. It should take us to this 1 here, reflect across the vertical axis. It takes us to this 0 here, and we reflect our direction across the vertical axis. We're moving down right. Again, this doesn't matter because we're on the last digit, but I want to be thorough. So 6 plus 1 is 7. 5 plus, so ignore that because we're modding 7. 5 plus 6 is 11. Plus 6 is 17, plus 6 is 24. Make sure I did that right. 6 times 3 is 18. Did I do my math wrong? I might have done my math wrong. 11 plus 12. It's 23. Did I say 24? I did say 24. 11, 17, 23. It is 23. Yes. So 23 mod 7 is 2. Because 21 is 7 times 3. So now we have this final sequence here. And what we need to do is convert each of these digits individually into 3-digit binary. So 110 is 6, 010 is 2, 011 is 3, 101 is 5, 000 is 0, 110, 010. Make sure I have the right amount of digits. I'm separating these out so you can see what I've actually done. There we go. 6, 2, 3, 5, 0, 6, 2. Now, final step. We're getting there. The final step we need to do is we need to add a 1 here, because it just says to prepend the binary sequence of the 1, and then we're going to convert this into a sequence of presses and holds, which is what we're going to actually input into the module. Now, the rules for this, I'm going to write them out here. They are explained in this paragraph, but I prefer to just write them out as rules. 1 wants to be I. 0 wants to be P. So I and P are the 2 letters we're converting this into, or this binary sequence into, to represent holding and waiting, or pressing and waiting. Why these letters were chosen, I'm not sure. However, there are some qualifying rules. I is always followed by P. PP followed by I. Okay? And then the last rule that is a little bit more confusing, P, a singular P, is followed, followed by I if even number of I's before. So we can see what I mean as I go through this. 1 wants to be an I, no reason it can't be. Same thing with this one and this one. Now we have 3 I's in a row, so even if this was a 1, it would have to be a P. 0, it wants to be a P, but we need to check this rule here. Write that down there. So P, we have an odd number of I's before. So that means that this rule does not apply, and we can put a P there. 1 is an I, 0 is a P. We have now 4 I's before, so this cannot be a P. This rule applies, so P is followed by an I if there is an even number of I's before. There is, this is an I. 1 is an I, 1 is an I. We have 3 I's in a row, so even though this is a 1, this has to be a P. 0 wants to be a P, However, we need to check the number of i's. We have 3, 4, 5, 6, 7. 7 is odd, so this is allowed to be a p. 1 is an I. 0 is a p. 0 wants to be a p. Check the number of i's. 1, 2, 3, 4, 5, 6, 7, 8. It cannot be a p because of this rule. This is an I. 0 is a p. 1 is an I twice. 0 is a p. Now we check the number of i's because we have another 0 that wants to be a p. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Make sure I counted that right. 3, 4, 5, 6, 7, 8, 9, 10, 11. That's correct. So this can be a p since it is odd. I and p. And then lastly, if there is an odd amount of occurrences of the letter I in the sequence, let's find out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's not true. If it was, we'd just stick an I at the end. We just put it right on. But that's not true. Now lastly, we need to... Yes, I know. This, by the way, you're realizing why this boss is hard, because this work all has to be done at the very end, once all the other modules are solved. So you need a lot of time to be able to do this. So now we need to convert this into a sequence A of holding, releasing, and waiting. You'll probably have heard in the background here, the module is pulsing. That represents one quantity of time, right? And that is, you can see it with the orbs flashing in and out. So we need to do things based on that quantity of time. I represents toggling. P represents waiting. I know that's unintuitive because P should be press, but it's the way the module works. So I is going to be hold. So I is going to be a hold if you're not holding it. It's going to be a release if you are holding it. So I'm just going to write this out in words, and you can see what we're going to do. Hold, release, release, I can spell. Hold, wait, wait, because of those two P's. So I've gotten through this much. Then hold, wait, release, hold, release, wait, wait. I've done this much. And one wait, by the way, corresponds to one pulse. That's what I'm talking about. That's a time unit. So wait, wait, then hold, wait, release, wait, hold, hold, no, hold, 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 release. Make sure I hold, release. Wait, wait, hold, wait, release, wait, hold, release. Make sure I'm not going to... This is a lot of work to put into a boss. I want to make sure that I'm not missing one. Hold, wait, release. Wait, hold, release. Good. Wait, wait, hold. I appear to have miscounted my eyes. One moment. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have made a slight mistake here. Hold, release, hold. Ah, I see where we went wrong. I said that this was a hold. It's not. So this should be hold, wait, release. Hold, release, hold. Wait, wait. Release. Wait. Hold, release. Hold, wait, wait. Release. It's hard to keep track of what is a hold and what is a release over these waits. Hold, release, hold. Wait, wait. Release. So I've gotten up to there now. Corrected. Wait, hold, wait, release, hold, wait, wait, release. So that's not particularly intuitive, but I hope you see what I'm saying here. Now, the way I actually like to write this out is with brackets and dots. So a bracket representing a hold, closed bracket representing a release, and a dot representing a wait. So this is far more intuitive for me. So the way I would write this out, this isn't anything in the module, but how I would do this is bracket, open, dot, dot, close, dot, open, dot, close, open, dot, dot, make sure, open, dot, dot, close, dot, I want to make sure I line this up, open, dot, close, open, dot, dot, close. I'm just going to copy this text here, make sure it lines up. I. Indeed, it does. And there is a wait at the end. That doesn't matter. It's just there. So now we get to input this into the module. The pulses are fairly slow, so if you're EFMing this, it's not that bad. I should be able to explain what I'm doing. So it's going to start off, anything with a hold release is effectively a tap. So it's going to start off with a tap hold within one pulse, then we're going to wait 2 pulses, then release. I'll explain it as I do. We'll do it after this next pulse. Tap hold. Wait 1, wait 2, release. Tap hold. 1, 2, release. 1, hold. 1, release, hold. 1, 2, release. And the module solves. Oh boy, am I glad that that was right. I didn't want to do all this again. Okay, that was a very in-depth explanation of how this works. I'm going to do another one, and I'm going to do this a bit quicker. Yeah. I'm just very happy that that was correct. Yeah, so I'm going to do another one. I'm going to do a bit quicker how you might actually do it. I would like to bring up the fact that there is a cheat sheet for this module, if that is something you are comfortable with. It basically, what it does is it creates a grid of this. It puts other versions of the grid around it with the Klein bottle flipping already done. It does make the process effectively similar to just doing black hole. However, I'm going to do this legitimately. I should point out, by the way, and I can use this as an example to demonstrate how to catch stages. I should point out that the way you select this module is a little bit unintuitive. If the yellow ring is around it, that's just a selection. The red ring would be an input, so careful not to click on it when there's the red ring, because that would be, putting in the answer. So now I'm going to delete all this, and do all this again. So red and orange, that is 1, 1, 0, 0, 0, 0, 0. Solve this module. Now this is going to be interesting. Red, no orange. Yellow, no green, blue, that is your color, no indigo, violet. Now let's say I missed that previous stage, this one right here. Then what I can do is I can click the module, and you see the orbs changed. And now they display that previous stage, this one here. You see the red and the orange are lit. So that's what your recovery mechanism is, but it doesn't go back further. So, at least to my understanding, does not go back further. And yeah, so make sure you catch it. Anyway, so I have that there. Solve another one. Binary is everything except for green, it looks like. It's going to be red, orange, yellow, green, blue, indigo, violet. No, I'm wrong. Red, orange, yellow, no green, blue, indigo, no violet. That's what I'm missing. Yeah. This takes practice to just kind of stare at it for a bit and see all the colors. They are moving quickly. Again, it's why I say the color find is useful. Now here's a case where I can also point out that you don't have to XOR this string as you go. You can just do it all at the end because of the way XORing works. If I have an even number of ones in a column, that's going to be a 0. If I have an odd number of ones, it's a 1. You can verify this if you want. 1, 1 is 0, and then that 0, 1 becomes a 1, just for that digit alone. So I'm just going to do that here. 1, 0, 1 is going to be a 0. That's an even number. That's just all zeros. This is an even number. That's an odd number. That's an odd number. So our final binary sequence is 1, 0, 0, 0, 0, 1, 1. Just double checking that. Okay. Split this up again. Let's see, how many colored spheres do we have? 1, 2, 3, 4. I count 5, perhaps? Wait for them all to show up. 1, 2, 3, 4, 5. Perhaps 5. 1, 2, 3, 4, 5. Yes, we have 5 blue. Again, wait till all of them are present because they disappear. 1, 2, 3, 4. Yeah, that's correct. So, once again, we are going to start, let me convert this, 0, 3. So x is 0, so we're in this column. 3 is going to be there. 5 blue, so we're going to be facing down left because we rotate from north. We're facing down left. Immediately we have to wrap. I kind of wish I'd gotten this one in the example I was doing first. Ah well. So our first digit is going to be 3. Then we move down left. That should take us here. It reflects across this axis. Takes us here. And our direction becomes up left. Our value changes. Let me put that there. Our value changes to 0. So we're now there, and we're moving up left. We have to rotate now. Rotate 135 degrees clockwise. We're now facing downwards. 6 plus 4 is going to be 10. Mod 7 is 3. We're going to go downwards again, because we move 1 past the squares we add. Then we rotate 135 degrees. We're moving up left. 5 plus 6 plus 3. It's going to be 9 plus 5 is 14. It's going to be a 0. We're on that 4. Moving up left. Rotate clockwise. 4 plus 0 plus 5 plus 3. 4 plus 3 is 7. 5 plus 0 is 5. We need to move 1 square beyond. It should take us to this 1. Reflects across this axis here. We end up at the 6. Our value changes to 1. We're now rotating counterclockwise. We're still facing to the right. Rotate 135 counter. We're facing up left. We have 6. Up left takes us to this 5, or it should take us to this 5. Flip across this axis. We end up at the 6. Moving down left. So 6 plus 6 plus 6 plus 6. We got this sequence before. Plus 5. Yep. Which is going to be 6 times 4 is 24. Plus 5 is going to be 29. I'm just going to be very sure of 18. Or 24. 29 mod 7. Thank you. 1. Of course. Just making sure. So that's digit 5. We're facing down left. We move 1 beyond. We end up on that 1. We're facing down left. And I realize now that I'm not entirely sure if I changed my R value. So this is the sort of thing that can happen. So I'm going to quickly run through everything I did. And this is basically what you have to do. So we were at that 3 facing down left. It took us to that 5. So we're facing up left. 6 plus 5. Is that right? Hold on. Down left. Takes this 5 to this 6. Down left. Up left. Plus 5 is going to be 11. And I think I've done this bit wrong. Haven't I? Yes, I have. Interesting. Pause this recording for a second. Okay, after quite a bit of testing to figure out what had gone wrong, I did find the issue. I'm just going to continue with this because, I mean, you saw how long it took to explain that. I want to do that again. Yeah, apologies for that. I think the other one was fairly informative. So yeah, we're just going to start over from the beginning of this one here. So we're at 0, 3. We're at that 3. We're moving down left because of 5 blue. Just make sure this is recording. Yes, it is. So we start with 3. Move down left to the 5. We then rotate across this axis here, so we're actually at this 6. The direction is upwards to this 5. Our value changes to 0. That's what I forgot last time. And you can see why this module is as tough as it is. If you're doing this legitimately, there's so many little intricate steps that are very, very easy to miss. So we rotate clockwise. We're now facing to the right. 6 plus, we move to this 4, reflected moves to this 0. This is going to be a 6. So then we move 1 beyond that. We're at this 3. We're facing to the right. Our R value changes. Don't forget that. We're facing to the right. We rotate counterclockwise. We go 3 plus 3 plus, it should be this 6. It gets reflected to this 5. Our direction goes from up left to down left. And our R value changes back to 0. So 3 plus 3 plus 5, move 1 beyond, is going to be 6 plus 5 is going to be 11, which is going to be a 4. Once again, that is 3, 3, and 5. This last 3, which is the last square we move on, doesn't count. We're moving down left from there. we need to rotate clockwise, facing upwards. 3, 1, 6, 2. Move 1 beyond. 3 plus 1 is 4, plus 6 is 10, plus 2 is 12. This is a 5. Facing upwards, rotate clockwise. 5 plus 6 plus goes to 3 there, and that doesn't change because we're on this middle row here. So it gets reflected, but doesn't do anything. But does change our direction. We're now facing upright. So 5, 6, 3, 0, 6. So 5 plus 6 is 11, 12, 13, 14. So this is a 6. And our R value changes, of course. It's the easiest thing to forget. And then we move 1 beyond that. We rotate counterclockwise this time from upright. We're facing left. 6, 3, 1, 5. Move to the 2, reflects to the 0. Our value changes to 0. 0, 4, because we're on the 6th digit. Once again, if it's not clear, we're doing this a number of times equal to the digit we're on. 6 plus 3 is 9, 10, 15, 19, which is going to be a 4. No, it's going to be a 5. Yep. 9, 6, 15, 19. Yeah. 12, yeah. And then we are rotating clockwise now. So we're facing upright from that 5 there because we moved 1 beyond. 3, 5. 3, we're now facing down right. Again, it doesn't flip, but it does do that. The direction does change. So 5, 3, 5, 3, 3, 0, 3. So 3, 6, 9, 12, 22, which is going to be a 1. Make sure I did that right. 13, 16, 19, 22 becomes a 1. Convert this to binary. And that's just 3-digit binary conversion. So we always end up with 21 digits. And we stick the 1 on at the beginning. Don't forget to do that. Just because every time you stick a 1 on. Convert this to I's and P's. I, P, I. Has to be a P because we have 3 I's in a row. This has 4 I's before it, so that's to be an I. P, that's an I. This is a P. We have 1, 2. We have 6 I's before this, so this is an I. This is an I. This is a P. I. Has to be a P. I, P. You can see this gets fairly quick once you understand the rules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this can be a P because we have an odd number. Once again, this rule does not apply in this case. This has to be an I, though. 1, 2, make sure I did this right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. And now I'm going to skip the whole thing about holds and releases because, again, I just find this more intuitive. So this becomes open, wait, close, open, close, open, close, open, close. For those of you that are curious, this method is actually from the module Xenochrist, is what uses this, and I definitely find it a more intuitive way to input a sequence like this. So let's see if we can finally close out this tutorial. After this pulse, hold, release, tap, 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 hold, 1, release, hold, 1, 2, release. And we have solved module. Oh, that is a relief. Okay, I hope you have enjoyed this. I do realize that there are modifications to Kugelblitz. If there are multiple of them, I am not going over them here. I will leave that for another qualified individual to do. Yeah, I believe, so they do not work just as individual modules. They all interact a bit like Twin, if you're familiar with that module, but that is beyond the scope of this already extremely lengthy tutorial. Again, apologies for the mistakes, but this is a very easy module to mess up. Hopefully you have learned a new module today, and thank you all for watching. Have a nice day.